So I'm Florian Levet. I'm part of the Jean-Baptiste Sibareta team at the Interdisciplinary Institute for Neuroscience, and today I will speak about my work on quantification of 3D single molecule localization microscopy data. So first, as a motivation, what is single molecule localization microscopy? I will go very fast on that. Basically, we are just able to activate only a small subset of the fluorophore, which means that even if each spot here is diffracted limited, we are able to precisely localize them by using, for instance, a Gaussian fitting. And in the end, we don't have images anymore, we don't have pixels, but we have point clouds. So it's been a decade now that I'm working on these kind of problems. First, in 2015, I released SR Tesseler in Nature Method, which was the first time where Voronoi Tesselation, which is a space subdivided technique, was used, and we find a way to generalize the way we use them in order to compute a local density and add this feature to the localization, and find a way to have a kind of normalization for that allow us to do some segmentation that was really robust to the localization density. The software was released at the time of the publication, and at the time it was only for 2D dataset, and only one dataset could be opened at a time. Then in 2019, I released Tesseler, which originated by my desire of using the Voronoi diagram in order to adapt the gold standard of fluorescence microscopy colocalization analysis with fluorescence microscopy, which is the Manders coefficient and the Pearson coefficient to single molecule localization data. So we don't have pixel, we have localization. And the idea was to use the Voronoi cell as proxy for pixel in order to find pair density per localization and adapt this coefficient. And at this time, it was published in Nature Communications. The software were released. We were able to do 2D and 3D analysis with several datasets, but there was no 3D visualization. And in 2020, I realized that it was really a nightmare to develop with my Tesseler shoot, because there was code that was almost 10 years old. The architecture was quite bad, and it was I could change a line of code and required 20 minutes to compile, so it was really, really annoying. And there were some limitation with my software and the one that were that were designed for single molecule localization microscopy analysis that were really very clear for me. So I decided just to redesign a new application, which would be called Point Cloud Analyst. So from scratch. And the first order of business that I took was having a modular design, so a plugin architecture. So now you can develop a plugin for adding features, adding GUI and all this kind of stuff. So the developer in me is really happy with that, because I don't need 20 minutes to compile anymore. Then I work a lot with the for visualization and interaction, because if you just render a point as flat when you are in 3D, you just have no idea of the depths, so it's really annoying. So you can first do some sphere and poster. So on the graphic card, you display the point as a sphere. It begins to be better, but still it's not perfect. So you can add a screen space ambient occlusion, some shading in order to have really a good appreciation of the depth of your localization. You can use a heat map rendering, which is a 2D projection, gives you an idea of the density, but on 2D with respect to the point of view. You can create objects, so have the surface, the volumetric representation of your object, and then you can also do some ellipsoid fitting in order to have a very different kind of representation and computation on the object. And then the software here, you can see it's very easy to change the LUT that you apply on the features that you loaded. You can use the histogram to do some filtering, duplicate the data very easily in order to do further analysis on some part. You can use a text box in order to change the histogram that you display. You can change the LUT very easily. I wanted something very easy to use for my user, for the life scientist. You can create a Delaunay triangulation here, show it. You have a histogram, log distribution. You can filter it, apply a cutting distance, create an object, create the object. So here's a different plugin. You have some features. You can switch the features, do the log display. You can right click on an object in order to save its position and then zoom directly on it very easily. It can be really interesting when you have a lot of objects in your data. You can filter again, have a high-low display because sometimes it helps to see the organization of your object. And then the last thing that I will show is a very easy cropping with the mouse with respect to some frames, so XY frame, XZ frame. You can very easily do the cropping in order to have some view on some specific part of your data. Another thing that I really wanted to, that came very early in defining the platform, is that I wanted every command to be internally handled as a JSON file, because it's first you can read it, and that means that now you can also record it, intercept the command and record it. So here I open already some data, I created a low-net triangulation, create some object that we can see here. And I will go to this tab here, which is the macro tab, and we see every command that I have done that have been recorded. So here, I transfer it to the runner. I will change the file to simulation 2. I run the macro, and then simulation 2 was open. The low-net triangulation was created, and the object was created also. So you can really keep all your workflow as macro, load them, and execute them. A big work that was done in this platform was for really the 3D segmentation of the object, because when I began to work on 3D, which was when I was developing Colloc Tesseler, the solution to do 3D analysis of single molecule localization microscopy were really, really long. And I don't want to spend 6 hours to do some analysis of not even 1 million localization. So I began to watch what was already developed by some people. I find a couple of libraries to do Voronoi in 3D developed in C++, like Voronoi++, which was fairly rapid because they are using some space subdividing techniques like grid or K-nearest neighbors in order to speed up the process. The problem is that with that, you expect an homogeneous distribution, while in single molecule localization microscopy, we have a highly heterogeneous distribution. So we cannot use this kind of solution. So I decided to take benefit of the fact that the low-net triangulation and Voronoi diagram are duals. That means that you can compute the Voronoi diagram from the low-net triangulation. And then from a point set, I'm able to use the CIGAR libraries that have a very efficient multi-threaded CPU algorithm to compute the low-net triangulation. So you can compute the low-net triangulation on millions of localization in a few 10-ish of seconds. And then use this low-net triangulation and the connectivity that the tetrahedron are providing in order to compute the Voronoi diagram on the GPU. And here you can see the Voronoi in 3D. So in the end, here, you can see it's real time. I will go to this button, I click it, it begins to do the Voronoi diagram in 3D. So for 1,600,000 localization, here you can see some microtubule with 4 million localization, where it required 1 minute and 12 seconds to compute the Voronoi diagram and the Voronoi density. And up here, it's done. So it was basically 20 seconds for 1,600,000 localization. So it's really fast, and you can really directly see the density that you have on your localization and do some thresholding and segmenting on this density. And here you can see the corresponding object with this case on the microtubules. So here I will show a few data in 3D. Come on, up. Where you can see some segmentation of mitochondria here, some microtubule in 3D. Here you can see that I managed to do to compute the overlap between two 3D objects. And here, for instance, it was done in the team. They managed to do a whole acquisition of a wholesale in-depth with single molecule localization microscopy that you can see here. So it's 10 microns. You can see that there is a lot of cluster on the cell membrane. So I was able to do a Voronoi 3D, segment the clusters, find the centroid, and then apply a Voronoi in 2D on a sphere domain in order to do the analysis of the organization of this cluster on the cell surface. And the last thing I will talk about with PoCA is that I managed to do some Python interfacing. So I'm very happy with that because PoCA is developed in C++, but Python is really important with all the scientific environment and all the scientific libraries that there is. And I managed to use NumPy arrays in order to directly call the Python interpreter from PoCA. So that means that I can run this kind of script directly from PoCA without needing to go to Python. and get the result. So here you can see, for instance, I did some sphere fitting and ellipsoid fitting on this point cloud. The point cloud was in PoCA. I send it to Python, did the sphere fitting on Python, and get back all the parameters in a numpy array to display it in PoCA. So in the end, this is a software I'm pretty happy with. It combines SR Tesseler and Colloq Tesseler, so my two precedent technique, but it also integrates other widely technique in the single molecule localization microscopy domain, such as DBSCAN or K-Ripley. There is a really improved visualization and interaction. It's very easy to use. It's fast and robust, can handle millions of localization in 2D and 3D for visualization and analysis. There is a plugin architecture which is good for developers. You can do the macro recording and you can communicate with PoCA, with Python, sorry. Here I just show that I did a small plugin in order to load Protein data bank files and display in PoCA. And PoCA is already available on my GitHub. Some part of the code source is already available also, and there is some installer for Windows. And that's the end of my talk. So if you have any question, don't hesitate.